All right, so let's start looking at binary ceramic structures, and let's start with the one that doesn't fit the schematic that I just showed you. And this is cesium chloride. So instead of forming in instead of the anions, so in this case chloride, forming into a close packed structure, in this case the anions form into cubic, simple cubic, right? So just the corners here, as you can see. And so this is simple cubic, and it also has what's called a simple cubic Bravais lattice because, and again, we can't think of this as BCC because even though it has the appearance of BCC, this ion and this ion are different. So they're different sizes, and so it doesn't fit that same schematic that we see. So instead, if we just look at one group of ions, we see that it forms a cube. And then if we drew the other, so in this case the cation, and we just drew a shape for that, that would also form a cube. It would just be offset by this distance. And so we can think of this as kind of interlocking cubes of cesium and chloride. And so in that way, it has a simple cubic Bravais lattice because we can describe it with simple cubic, but instead of one atom per position, we have two. We have this and we have this one, and that would get us to the cesium chloride structure. So this is cesium chloride, the structure. So it doesn't just have to be cesium and chloride, it can be other compounds, but what we're referring to here is the structure that it forms. So this cubic Bravais lattice with two ions that are roughly the same size. All right, so in this case, let's look through a couple things. So in this case, it doesn't actually matter which one is the cation, which one is the anion, because it could be reversed, but this one is the cation, this one is the anion. So that's cesium and chloride. Coordination, this should be pretty easy to tell, because if we look at the cation and we look at what surrounds it, right, there's 8. And so we can expect that if we go to one of these other positions, we'll have the same coordination. So they're actually both a coordination of, didn't have it here, coordination of 8 in this case. And again, keep in mind that the larger the coordination, the larger that cation to anion ratio is, so the larger the cation is in this case. So that means that in this case, the reason it's not fitting with our scheme that we talked about with the close packed structure is because we're breaking kind of that general rule that we heard of with the anions being much larger than the cations. Here, the cesium and chloride are fairly similar in size, and so instead of forming a close packed arrangement of the anions, we form an arrangement with both of them being roughly the same. So that's the big difference between those two. All right, so let's go ahead and do a quiz question real quick. So down here, I've written, or I've shown you 4 structures without telling you what they are. So this is, I just want to see where you're at, how much you already know about these structures. So for each of the structures, see if you can guess what structure it's called. See if you can determine the coordination numbers. So that's for the cation and the anion based off of these pictures. And also, we talked about that polyhedra sharing. So once you've determined the polyhedra shape, see if you can determine how those are shared. And so for this one, it can sometimes help to draw it or print it out and try to sketch in the shape so you can see where they're sharing. So see how much of that you can get. I'll have this on the quiz, and then we'll come back and we'll start going through these structures one by one. All right, so let's go ahead and look at these in order. So the first one, this is the rock salt structure. So that is the structure of sodium chloride that we've talked about extensively in the bonding chapter. And so this does fit into that scheme that we talked about in the previous modules, where we have a close packed arrangement of the anions and then filling of the cations. And so in this case, the chloride forms in the FCC arrangement And then we have sodiums in the octahedral sites, and we have it in all of the octahedral sites. So if you kind of look at these 6-pronged things, everywhere you see one of those, that's where we're putting one of those. So if you kind of draw that out, you see that this is the same as filling up all the octahedral sites in this case. And so for this structure, again, chloride is in an FCC arrangement, and also in this case, the sodium is also in an FCC arrangement, just shifted. So we can also think of this as interlocking FCCs, and it's just shifted by the unit between two atoms here. So in this case, the Bravais lattice is FCC because we can describe it as FCC, but instead of one atom per point, we have 2 ions per point, and that will give us the rock salt structure. So it's a FCC Bravais lattice. However, it's important to know that even though the anion, we say that that's in the FCC arrangement, it doesn't mean it's close packing anymore. Because once we put cations in these interstitial sites, these sites are not actually big enough to account for the cation. And so it expands that structure out into something bigger. And so this is no longer close packed. We can also kind of prove that to ourselves by looking at the coordination, right? The coordination of each of the anion or cation is 6 and not 12. And so, again, even though we think of this schematic as close packed arrangement of the anions, once we put cations, it actually expands out the structure, and so it's no longer that close packed structure. So it's more of just a way of thinking about how these structures are put together. Okay, so examples of this sodium chloride or rock salt structure are most of the first row transition metal, what we call monoxide, so one oxygen. So this is iron, FeO, iron oxide, cobalt oxide, manganese oxide, nickel oxide, all of those with one oxygen and one metal. And then also, if we go to the next slide here, we can see the polyhedra sharing. So these are the octahedron that we see if we sort of sketch them out from over here. And in this case, you see the sharing along the edge. So here we have edge sharing polyhedra. So this can be difficult to see from this diagram, so sometimes I recommend actually sketching out those polyhedra if you can.